So today what we are going to practice is work, power and energy. So I start with you people, like what you know about work? What is work? Write in the chat. I say Fatma. Just That's right, Fatma. Isil, what you know about work?
Everything else.
Sorry?
And give you the answer in the chat. Let me see.
Like from the concept of IGCSE. Okay, if you have written in the chat, maybe I have not got it. Can you write it again, please? What you have written is right, but here we need to be careful about one part of that display, that formula or that statement very carefully. No doubt work done is equal to force times the displacement. But here at AS level, we need to explain what displacement or in like which displacement. So do you have an idea? Anything special about that displacement? Is it just the displacement or any particular displacement?
Just the displacement.
No, it is a particular displacement. If it's displacement other than that, we are not going to include that. So it's a particular displacement, and what's particular about that? In the direction of force. Or it can be the component as well. May not necessarily be the whole displacement. Displacement or the component of the displacement which is in the direction of the force, we only pay attention to that. It's a really important point for this thing, because most of the time students make that mistake here. So whether it's the whole force displacement or the component of the displacement, component we have discussed rectangular component, or a component of the displacement which is in the direction of the force. What does it mean? And we are going to write the formula like previously from IGCSE. The formula which you may have learned is work equals to F times S. No doubt it is F times the S, but this S again must be described as we have described. So how are we gonna describe it in the formula? So to explain that how we gonna describe it in the formula, have a look. If say that we have we pull an object in a particular direction with some force in this direction, and the object moves in another direction. So just a moment. So say that the object goes in that direction. Okay. So what happened in that case? I just use arrows. So these are the force. One is the force and other is the displacement. Say that if they are not along the same direction, we exert a force and the object moves in a different direction. So we exert a force in that direction, the object moves in that direction. So what's gonna happen in that case? It's not gonna be simply force and the distance, because distance is not in the direction of the force. So what we're gonna do, we're gonna resolve our distance into two components. We are going to resolve our distance into two components. And what are those two components? Those two components, one in the direction of the force, which I highlight with the red color. So I just also make them a little, just a second. So one component of that force is in the direction of the, one component of the displacement is in the direction of the force, and the other component is perpendicular to the force. Is that right? So that's what we need. So this displacement vector is split into two parts. One in the direction of the force, other perpendicular to the force. So which component we will use? We'll use a component which is in the direction of the force. So how we work it out? We always say that what's the angle between the force and the displacement. So if this is the angle theta, then the component of the displacement in the direction of the force is s cos theta. So it's not s, it's the s cos theta, which is in the direction of the force, and it's the component which is perpendicular to the force is s sine theta, because it's opposite to the theta. The component adjacent to theta is the cos component, and the component opposite to theta is the sine component, right? So that's how our formula get modified. Our formula get modified as work done is equal to Fs cos theta. What cos theta is representing? That component in the direction of the force. And what theta is representing? Where theta is the angle between force and displacement. So if the force and displacements are making an angle theta, then we use Fs cos theta. Is that right? Is that clear, this part?
Yes.
Okay, that's great. Now, according to physics, although we are practicing physics right now, but according to physics, are we doing any work? Are we doing any work right now? We are studying physics, we are practicing physics, but are we doing any work according to physics?
No, because we're not moving.
That's right, because the displacement is zero. So that work done by us right now is zero. It's a bit unjust. We are practicing physics and physics says, okay, you are doing no work. So let's see, well, like a little later, how unjust it's gonna be to another person, and we'll see then later on that what's the issue with that. So do you know what are the unit for the work or energy? What are the units? Write in the chat. The unit for work or energy, what are the units? That's right, Aisel. That's right, Fatma. That's good. So do you know in break, like if I want to break a joule, what a joule is equal to? If I want to write the components of the joule, it's the unit of the force and displacement. So what's the unit of the force? It's Newton. And what's the unit of the displacement? It's meter. So Newton meter collectively called as joule. Remember, both force and displacement are vector quantity. Force is vector, displacement is vector. But work is scalar. Force is vector, displacement is vector. Both of these quantities are vectors. But you need to remember, work is a scalar quantity. Work has no direction. It has just the magnitude. Work is a scalar quantity. I will go to my example, which I want to actually emphasize on work. But before going to that example, there's a very simple thing, and although it's a topic in AS, and it's a really simple thing, you may have an idea from IGCSE, but I do, whenever I teach the student about the AS, like this work energy, I do mention that's the simplest thing, and that's the most common thing students don't use in exam. It can be used in many questions, but students have no idea that, okay, you can use this and you can get your answer. And that's called work energy principle. So do you have an idea what is a work energy principle?
No.
Okay, no problem. Like I said, it's a really simple thing. You may have an idea, but you don't know that it's called as work energy principle. Simple. Work done equal to energy transferred. It's the simple thing. Work done is equal to energy transferred. Work done is equal to energy transferred. If there is a work done, there is an energy transferred. And if it's both ways, it goes both ways. It's not just one way. This thing which we are practicing is both, it goes both way. That if work done is equal to energy transferred, then it means energy transferred is equal to work done. It's a cyclic statement, and it's a principle. It's always applicable. All the time, this thing gonna be applied in well good spirit, like that. So it goes both ways. If work done is equal to energy transferred, then energy transferred is equal to work done. All the time, not in one case, not in two cases, it's all the time like that. Work done is equal to energy transferred, and energy transferred is equal to work done. So we will come back to this because I want to discuss this thing in detail, but right now we are going to just focus on our the other thing which we have mentioned in the beginning, that is the displacement in the direction of the force. So if we look at that part and we just use this, so be careful what I'm going to practice. You can, for disconnectivity again, disconnectivity. Can you hear me now, by the way?
Yes.
Okay, that's good. So the example which we are going to practice on next page, it's gonna address three things. It's gonna address that component in the direction of the force. Okay, we are going to discuss this thing in detail. The second thing it's gonna focus on this work energy principle. The third thing is that how important is it to read the statement? Importance of reading statement. So three things: component in the direction of the force, work energy principle, and reading statement. Sometimes students never pay attention to the statement. Okay, so I have intentionally mentioned you that what I'm going to practice these three things in the next example which we are going to practice together. So what is the importance in case of the work done of the distance displacement in the direction of the force? What is the importance of the work energy principle, and what is the importance of reading the statement carefully? So what example we are going to practice here? Let's say that we have a weightlifter who is going to lift a heavy load. So the weightlifter is on a ground, which is this. I draw the ground first. So on that ground, the weightlifter has some heavy loads connected to the two sides of the bar. So this is one side, and I just remove the bar and draw the side of the bar as well. So that's how the person's practice in the gym. So there's another weight on the other side. So I draw a stick diagram. Approximately a person has a 6 feet height, so he can lift the load to 6.5 feet, which is approximately 2 meters. So say that our stick diagram person is this. And this is the person. So when he lifts the load, the same load which is down will go above his head height, right? When he lifts it up, it goes to the head height or like that. So he lifted it like just lifted like this much, and this is the load which he is going to lift. So this load he is going to lift, and as he lifts, it goes to the head height. So say that the weight of that load, carefully listen, and I will write these values as well. The weight of the load is 2000 Newton. The weight is 2000 Newton. The height lifted is 2 meters. Weight is equal to 2000 Newton. Height moved is just 2 meters. So I will ask you some simple questions. They are not difficult, but instead of just asking you the question, I'm going to write the statements. So the first question: Okay, I helped you a little. What shall be the expression? What is the expression if object is lifted? What is acceleration? If object lifted up with a constant speed. So can you tell me the answer to that part? If the object is lifted up with a constant speed, what will be the expression? Write in the chat. That's right, Fatma. Aisel, what will be the expression if the object is lifted with a constant speed? Okay, even that's right, but can you tell me the magnitude? How much will be the magnitude? It will, no. Constant speed, is speed changing? So what will be the value of the delta V then? What will be the answer of delta V, Aisel, then? 0. So what will be the expression? That's right. The expression is 0. Right? So A is equal to 0. Is that okay? So if this is 0, the next question, what will be the resultant force? Resultant force acting on the object. What will be the, what is the, I just write it in the then what is the resultant force acting on the object? What is the resultant, as we are lifting it up, so what is the resultant force acting on the object? That's right, Aisel. Now, sorry, you have given the answer to the previous part. So what will be the resultant force, Aisel and Fatma? If acceleration is 0, what will be the resultant force? That's right, Aisel. Fatma, what will be the resultant force? F is equal to ma is for resultant force. So if A is 0, what will be the resultant force? That's right. Resultant force will be 0. So to make the resultant force 0, how much should be the upward force? So what will be the upward force acting on it while we are lifting? What is the upward force? So as we are lifting it, weight is acting downward, which is 2000 Newton. So how much force should be acted upward to lift it with a constant speed? That's right, Aisel. Fatma, what should be the result upward force? To make, as the weight is downward, upward force is 2000 Newton. That's very good. So upward force is 2000 Newton. That's really good. So these are the things, and the height here it has moved up is 2 meters. So you have these things right in front of you. So now I write the other questions again, because like I have said, we are going to practice a lot of statement. So I'm writing the statement instead of just asking it. So the next statement is, now we are going to calculate the work. Work done on the load while lifting it. We have to use the applied force in this case, not the resultant, because we are calculating the work done. Work done on the load while lifting it at a constant speed. We are lifting it up, but we are lifting it at a constant speed. So what you think, both of you, what will be that work done? By 2 meters. I do write by 2 meters. That's the height. That's right, Aisel. That's right, Fatma. So that is, we will use the formula work done is equal to force times the distance, displacement, and what gonna we get? We get 4,000 Newton. That's the right answer. Now, the person has already lifted that load. The question is, the next question which we are going to ask is work done on the load while holding it above the head height. Work done on the load while holding. He not drop it down, he not move it further, he not move left or right, he just hold it there. Work done on the load. That's right, Fatma. While holding, that's right, Aisel, it above the head height. But can you tell me what's the force he is exerting even then if he's just holding that load above his head? That's right. That's right. So still the force he is applying is 2000 Newton, but the displacement he is just holding it, so that's why it's 0. So that's right. Work done is 0. Actually, it's 0. Okay, now that's good. So the next thing which we are going to practice is work done on the load while holding it above the head height and moving 20 meter to the right at constant speed. Work done on the load while moving work done on the load, yeah, while moving 20 meter to right at constant speed, keeping the load above the head. So how much work done right now? Okay, Aisel has given her answer. Fatma, what do you think? Yes. Why you Aisel has given a 40,000 Newton. Fatma has given an answer of 0. Why, Fatma? Why you are getting 0?
Because the force is 0.
No, force is not 0. He's still holding the load above his head. So if he stop exerting the force, it will fall down. Yes, Aisel, now you got the answer. Distance is not in the direction of the force. If you use the angle, force is exerted upward and the displacement is covered to the right. So what will be the angle? What will be the angle? If the force is upward to hold the load above the head height, we need a force upward. But we are moving to the right. So what's the angle between the force and the displacement? So we do have the force, we do have the distance, But the angle, what's the angle right now? If we are exerting the force upward and moving to the right, so what's the angle between the force and the displacement? Look in the figure. I draw in the figure as well. Just so we are exerting a force that is upward. Yes. So if you put cos 90, what you will get? 0. That's the reason. Although you have the force, although you have the displacement, but still it's 0. Why? Because the force and displacement are at 90 degree. So the cos 90 is 0. Is that clear, Fatma?
Yes.
So that's what's happening here. Although we are exerting force, although we are moving some distance, but the force and the distance are at 90 degree. So that's why the work done will be 0. So we put the values. We do have those values. 2000 Newton times the 2 meters times 20 meter, because move 20 meter, but cos 90. So that give us 0. Got it? We will explain it later as well. So this is the first part. We should not use any distance. We should use the distance in the direction of the force. So object has neither moved up nor moved down. So there is no distance or displacement that is covered in the direction of the force. It has neither moved up nor moved down. Got it? Is that part clear?
Yes.
So the next is work done on the load while lowering it down. While lowering it down by 2 meter at a constant speed. So what you think? Okay, for this question, first you tell me how much force and in what direction do we need the force? For this last part, how much force and in what direction do we need? Okay, Fatma, what you think? How much force and in what direction? Fatma, what you think? How much force and in what direction we need that force? Aisel, I can see your answer, but we will discuss it in a moment. Fatma, can you hear me?
Yeah.
Okay, how much force and in what direction? No. Both of answers. The trick is constant speed. Still, we want to lower it down with a constant speed. So what will be the expression? Repeat the same questions, and you have to repeat the same answer. If it's constant speed, what will be the acceleration?
0.
0. If the acceleration is 0, what will be the resultant force?
0.
So what should be the upward or downward force which we should exert to keep the resultant force 0. Weight is downward 2000 Newton. So in what direction, how much force shall we apply to make the resultant 0? How much? I feel that's the right direction, but how much? To make resultant 0, 2000 Newton weight is downward. So to make resultant 0, that's right. So Fatma, what should be the force and in what direction? How much force in what direction to make the resultant 0 if the weight is downward? Because if you exert a force downward, no, not 0 Newton. If you apply 0 Newton upward, weight is 2000 Newton downward, so the resultant force will be 2000 Newton downward. Like you drop an object. 0 Newton is the case when you just drop an object. Say that you have a glass, a water glass in your hand, and you want to just place it gently on the floor. So will you stop, like, will you just release it, exert no force on it? Or will you lift it up? Or like you place your hand under it? Where you will put your hand? If you want to lower it down so that it not fall or break, will you place your hand on the top, on the bottom, or will you not place your hand anywhere? If you want to lower down a glass, where you will place your hand? Below the glass, above the glass, or you will not touch the glass? What you will do if you want to lower down a glass of water, what you will do? Or a bowl, anything, you want to lower down a bowl to the ground so that it may not break. So will you place your hand under it? Will you place your hand on the top of it? Or will you not touch it and just let it drop?
Under it?
Under it. So when you are under it, you are actually pushing the ball upward. You are exerting a force upward so that it may not fall. Although you let your hand go down, but your hand is always pushing the ball upward, isn't it? You move your hand down, you are not holding the ball, you are just supporting the ball that it may not fall. So your hand is exerting a 2000 Newton, like in this case of the load, the person is still exerting a 2000 Newton force upward, because if he just release it, that load will get smacked on the floor. He don't want to do that. He want to just lower it down at a constant speed. Got it? So he needs a 2000 Newton force upward. How much this is that clear, Fatma? 2000 Newton upward? Okay, that's right,
Yes.
Aisel. Let me know, Aisel, just get out of it and let me know, Aisel, when you are back. So Fatma, is till then, is there any question from what we practiced till now?
No.
Okay, and just on the sideline, are you practicing any like past papers, any topicals?
Yes.
Okay, and you are getting confident, like, are you getting your like questions done, or you are facing problems?
Yeah. Yeah, it's going fine.
Okay, that's great. Just wait. Okay, nice. that's good. Just a second. So now be careful. To lower down, the distance moved is downward. The force is upward, but the distance moved is downward. So what will be the work done when we lower it down 2 meters at a constant speed? So in that case, what will be the work done? Okay. No, that answer is not right. Angle is not zero. Magnitude is right, but angle is not zero. One force is upward and the blue arrow is downward. So what's the angle? The 2000 Newton is still upward. But the displacement is downward. So what's the angle between the upward 2000 and the 2 meter downward? What's the angle in between these two things? What's the angle? Aisel and Fatma? If the force is upward, displacement, yeah, use that 2000 Newton is the force, 2 meter is the distance or displacement, and 180. Yes, that's the right answer. Fatma, are you there?
Yes.
So what answer you will get if you put these values? 2000 Newton upward, 2 meters downward, and angle is 180. So Fs cos theta. Not this, cos 180. You have to use cos 180. Work done is equal to F times the S times the cos theta, which is 180. Fatma, check your answer again. Fatma, are you checking your answer? No. Magnitude was right. Cos 180. What's the answer of cos 180? Check it out on the calculator. Minus 4,000. Yes, so 2000 times 2 minus 1 is minus 4,000. So that's the work done. So, right?
Yeah.
So we have paid attention to the displacement in displacement in the direction of the force. We are now going to explain how this example, like I have mentioned it, I'm going to address three things. So we have addressed one thing, that we need the displacement in the direction of the force. How the other two things are discussed here, that is work energy principle. And that will actually explain another thing here, why that negative, or what's the meaning of that negative here. I intentionally kept something clearly written. Constant speed or holding or constant speed or the constant speed. So if the speed is constant, will be there any change in kinetic energy?
No.
So that's why we have written it, to make my other problem easier. I kept my speed constant, so I should have not, I do not need to address any change in kinetic energy. So for all these statements, the change in kinetic energy is 0. Is that right? Is that clear? For the whole statement, what I have discussed, the change in kinetic energy is 0. Is that okay?
Yeah.
Only change in this example is the change in potential energy. Change in GPE, because the height gets changed. So can you check, if you lift an object with a weight of 2000 Newton by a distance of 2 meters. So mg is 2000. So first of all, when the load is on the ground, what's the potential energy at the ground? At the ground, what is the potential energy? GPE. When the load is at the ground. That's right. And when you lift that load by 2 meters, what will be the potential energy? mg is 2000. You lift it to a height of 2 meters. So what's the potential energy at the top? And B position, that's A position, and we are talking about the B position now. So what's the potential energy at the second, B position? I write it not 2, I write it B. So what's the potential energy at B position? Weight is actually mg and the displacement is height. So you have the value of the mg already and you have the height as 2 meter. So what will be mgh at B? That's right, 4000 joule. So what's the GP change in GPE as we move from A to B? What is the change then? That's right, Fatma. I said, what's the change? At A, it was 0 joule. At B, it has changed, increased to 4000. So you can see that isn't the work done is equal to the change in potential energy because the kinetic energy is 0. So all the work which we do actually get transferred into kinetic energy. Oh, sorry, potential energy. Is that right?
Yes.
In the next case, there is constant speed. So what will be the change in kinetic energy? Oh, sorry, holding. But yet we have to discuss the holding. If we are holding it, so is there what will be the change in kinetic energy? If we are just holding it, will be there any change? That's right, no change, 0. That's true. And if we are holding it, there is no change in height. So will be there any change in potential energy?
No.
So you can see that no change in potential energy, no change in kinetic energy. That's why no work done. Because work done is equal to energy transferred. If there is work done, there must be energy transferred, or reverse. If there is an energy transfer, there must be work done. So if there is no energy transfer, like in this case, no work done, and that's the same thing in the next case. It's constant speed, so change in kinetic energy is 0, and keeping the load above the head height. Keeping the load above the head. So if we keep the load above the head, will be there any change in height? If we just keep it above the head, no matter how much he moves to the left or right, he just keep it above the head, will be there any change in height? That's right, there will be no change in height. So if there is no change in height, will be there any change in potential energy? Will be there any change? That's right, Fatma. Aisel, will be there any change in potential energy if there is no change in height? So no change in potential energy, no change in kinetic energy, so no energy transferred. So if there is no energy transferred, how much is the work done? 0. Got it? And
Yes.
now for the last case, we move from B back to A. So at B, initially its energy was 4000. When we move it to A, its energy is decreased to 0 joule. So how much is the change in potential? Because it's moving with constant speed. So change in kinetic is 0. But how much is the change in potential? It moves from a height where its potential energy was 4000 to a point where its potential energy is 0. So how much is the change? Final minus the initial. That's right. Is it positive or negative, Fatma? I said your answer is right. Is it increased or decreased, Fatma, as we move it down? It's decreased. So decrease will be shown with a negative 4000. Its energy has been decreased by 4000 joule. That's what it's here. Got it?
Yeah.
So we discussed two things. We discussed the cos theta, that's the component of the force in the direction, component of the displacement in the direction of the force. We discussed the work energy principle, that is, work done is equal to energy transferred. Now the third thing. But before going to third thing, what you think? Isn't it quite weird that if the person holds that heavy load above his head, he will get tired, and if the person walks 20 meters to the right, he will tired even more. But physics is saying no work done. What's the case? Can you explain this thing? Person will definitely get tired even if he's just holding the load above his head. He get exhausted, and if he walks to the 20 meter to right, he will get exhausted more. But why the work done in our calculation is zero? Can you identify something? The calculation says the work done is zero, but we know that the person will get tired, person get exhausted. So how is that happening? Why the physically person is getting exhausted, and why the mathematically the work done is zero? You can unmute yourself and discuss this thing. Is there any answer you have? Any of you? Any explanation to that part?
Person is still applying a force to hold it up.
Yeah, but work done is zero. So why he is getting exhausted? He is applying a force, no doubt he is applying a force, but no work done. Or is there any work done? Especially when he's walking to the right. Do you know? Okay, just a second. The person is still applying the force, but okay. You know the tricky part? This calculation was not the calculation of the work done by the person. Look at the statement. That's the third thing which I mentioned. That what we are going to look, we are going to look at the reading the statement carefully. So am I calculating the work done by the person or on the load?
Of the load.
So there is no work done on the load, but yes, person is doing work. Even if you start walking just without any load, are not you doing any work? You are doing a work because you push the ground and ground pushes you forward and they are in the same direction. Got it? 180 degree or like that. So you do the work against the friction, right? So even if you are not lifting any load and simply walk, you are doing work against the friction. Got it? Like I always, to understand the friction, I give the example to the student. Ice. In real life scenarios, ice, not snow, but ice is almost an example of frictionless surface. So what you think? Once a person or a car starts skidding on ice, will it stop? Like if you take one step on ice and you start skidding, will you get stopped unless you hit something?
No.
So you don't need any force to walk or skid on the ice. But on the ground, you need the force to move. You need to do some work against the friction, to overcome the friction. So you do the work even just walking simply. Got it? So person is doing the work while walking because he is pushing the ground backward and ground is pushing him forward. So there is a negative work done, that like a work done, and the distance, the force exerted by the person, and they are in the opposite direction, right? Or the there is a work done. Now how I can explain the person is doing the work, like in a sense that he's just holding the load. He's just holding the load, but in this case, the energy which is being transferred is a different kind of energy. It's not a mechanical energy. Do you know, in like if you go to a gym or an exercise club or like that, when you do exercise, what happened to your body? Your body warms up. isn't it? Are you familiar with that? We call it warming up or like that.
Yes.
So when you are holding the load above your head, your muscles are not in a relaxed position, they are in a stretched position. So when the muscles are in a stretched position, they do different kind of reaction inside the body, which makes your body warm. So the work is actually used in a different way to keep the energy. I will not call it work. Why the person will get exhausted? Because his energy is used to make his body temperature rise. So he's not doing a mechanical work, but the energy is why he is getting exhausted, because his energy is used to make his body temperature rise. As his body temperature rise, his energy is utilizing. He is using his energy, the food energy or whatever energy in the muscles. Your muscles can have fats or like that. Our muscles itself has energy, like we carbohydrates. Our body has carbohydrate, fats, and proteins. Right? These things do have energies. So when we consume them, our body temperature. So person get exhausted not because of the work, but because of the thermal energy. Got it? So that's the key line. So you need to think of these small steps. So this is a perfect example which I always teach the student like that, that you need to pay attention to the statement. I give you the statement of the work done on the load, and where I confuses you that why it's unjust, person is getting tired. So I'm asking you the work done by the person. So in calculation, I was calculating the work done on the load, and while confusing you, I was like I say that I'm successful to make you confused by saying that okay, a person is like getting exhausted, and the physics says that he's not doing work. No, physics says that there is no work done on the load because the kinetic energy or potential energy of the load is not increased. Got it? So you need to pay attention to all these things. Is that clear?
Yeah.
So any question about this thing? Is there any question about this thing which we have practiced?
No.
Okay, so just okay. So now we just mathematically also prove. Do you know the formula for potential energy and kinetic energies? What are the formulas for potential energy and kinetic energy? First, we discuss the formula for potential energy. Do you know the formula for potential energy? Although I have used it, and I'm asking it again, but no problem. Formula for the gravitational potential energy. That's right, Fatma. Aisel, what's the formula for the gravitational potential energy? Okay, that's just a second. That's right. So if we want to lift an object at a constant speed, so that work which we do is only the potential energy thing. So the force which we need to lift the load is equal to the weight, which is equal to mg. And the distance which we move is always equal to the height. The distance which we move is always equal to the height. So they are in the same direction, so we can just use the simple formula for the force and the work, that is the force and the distance. So in that case, what will be the work done? Force times distance if they are in the same direction. Even if you put the cos theta, it will be cos 0, which is 1. So force times displacement and cos theta, I do put it. So what we will get? Force is mg, the displacement is h, and cos 0 is 1. Got it? So what we get? We get work done is equal to mgh. So that is the work done goes to change in potential energy or the change in potential energy. That's why we say that work done is equal to potential like change in energy. Got it? Because work done is energy transfer. Is that clear for this in potential energy thing? And in very simple, although I have discussed it, I'm pretty sure you have an idea, like you have given much more answers. Can you simply define in one line what's potential energy or what's gravitational potential energy? What is gravitational? Define gravitational potential energy. How you will write? Waiting for your answer. Define potential gravitational potential energy. Oh, the Fatma, or you confuse it with the kinetic. Kinetic is a word which is used for motion. Kinetic is a word which is used for motion. So if object moves, it has kinetic energy. Fatma, energy due to position, right? TPE is energy due to position. Okay, so the next thing is define kinetic energy. Although we have discussed it, but you can quickly define it. Yeah, change in motion or just due to energy due to motion. Fatma, energy due to motion. Now, one can say that, okay, and I just actually need one more thing because I just thought these things are too simple. That's why I have not discussed in the beginning. But now somehow I need these basic definition. So the one next thing which I need is simply how you define energy. Whether it's potential or kinetic, that's a different thing. But how we define energy? What is energy? That's right. Capacity. Fatma, I'm waiting. Is it Fatma, I'm waiting for your answer. What is energy? So, being able to do work or capacity to do work or ability. So, I define it. All of you, what you have mentioned is right. So, actually, energy is ability to do work. If an object has some ability, no matter it's due to motion or due to like a position, we say that it has energy, ability to do work. So to explain this thing, this definition I just mentioned you, that say that the work which we want to do is pinning a nail into a wooden block. We have a wooden block and we want to pin down a nail. So to pin down that nail, we need to do work. We need to exert force and we need to move the distance, like nail to move some distance into the wooden block. Say that this is the wooden block, I make it a little block. Say that this is the wooden block and we have a nail here, just a second. We have a nail here and we want to pin it down into that wooden block. So can we really do it with our hand? If we start pushing it with our hand, will we be able to do that? What do you think? Can we do that with our hand? Can we pin that nail into the wooden block with our hand? Like completely push it down?
No.
That's the right answer. We cannot do it. So what we use to do this? A hammer. We use a hammer. So what you think? Do you really think it's the hammer which can pin down the nail or is it something else? If I just place the hammer like this, will it be able to pin the nail down no matter how hard I push? Will it be able to do? Okay, we can apply the force on this hammer with our hand, a lot of force with our hand. What you think? Will it be able to still push the nail? We can push that hammer down really hard. Push. Be careful, I'm using push. So if we push with our hand a lot of force on that hammer from the top, what do you think? Will it be pressed down or not? Will it press down the nail or not?
Yeah.
No. We don't push the hammer. We never use the hammer to push something. Rarely we do it. What we do with the hammer, we hammer it. We not push it, and what does it mean? That you move it back and strike it. Right? So hammer don't have the energy to push that nail into the wooden block, but moving hammer does. Got it? Got the idea? Moving hammer, the movement of the hammer is must. You can't just push it. Got the idea? So moving hammer has the energy or has the ability to do that work. But a static hammer, no matter how hard you push it, it don't have that energy. Got it? So moving hammer has the energy, hammer don't have the energy. Got the idea? What's the ability to do? When it's moving, it can do the work. When it's not moving, it cannot do the work. So that's what we mean, ability to do work. That hammer has the ability to do work due to its motion, not just because it's a hammer. Got it? So such thing is called ability to do work, which is the energy, and that's so now we have already discussed the potential energy formula that in lifting an object we get mgh. Now how we get half mv squared? So for that, while calculating the mgh, I kept one thing constant. What I kept constant, I have mentioned it here or not. We said that we lift it with the that we need a force equal to weight. So if the force is equal to weight, resultant force will be 0. If resultant force is 0, acceleration is 0, it means there is no change in velocity. Okay, so that means there is no change in kinetic energy. So we actually kept this thing in this simple discussion, that to discuss the potential energy, we keep the kinetic energy 0, like change in kinetic energy 0. So in this case, that when we are going to work out the kinetic energy thing, we will keep the potential energy, change in potential energy 0. And how we can do that? We can do that by throwing an object horizontal. So again, sometimes in the beginning, someone said even right now you said the hammer has the ability to do work, not to push the nail, or like it was not the hammer. So simply I say that, do you have enough force to do you have any small keychain or like any key or any small ball or like a pen cap right now near you? Any small thing which you can grab easily in your hand? Is that so? Any key, any small object, pen cap or like thing? Is it there? Can you get
Yes.
that? So just simply, not very high, even just like half a foot is enough. You just toss that thing up and you can easily catch it back. So you can throw this thing up. Is that right? You have the force to throw it up. You have the energy to throw it up. Yeah, rubber will do fine. Can you do that? Can you throw it easily? You have the force to throw it. You don't have a force to throw the table, but you have a force to throw that rubber or pen cap or like that. Is that, do you have the force or not?
Yeah.
Okay, that's
Yeah.
good. But be careful, it was not only the force which throws the object. Now I say that, give you a task to throw the same object but with another technique. The technique is, you can exert as much force as you want, like you can grab it in your hand and crush it. You can exert a lot of force on it, but the task is, try to touch the back of your hand with the table. Before you throw it, try to touch the back of your hand with the table, and your task is that your hand should never leave the table. So you can crush it. You can exert a lot of force and press that object in your hand, but if you are not allowed to leave your hand from the table, will you be able to throw it?
No.
Simple as that. So it was not the force enough to do work. No matter how much force you exert on the object will not move. You are not able to do any work, because work is not just the force. Work is force times the distance. I put a condition that your distance must be 0. So no matter how much force you exert, the work done by you on that object will be 0. Got it? So when we throw the object, we do the work. If we throw it upward, it gains potential energy. But if we throw it horizontally, like to throw horizontal, what we do, when if we want to throw a ball horizontally, then what we need to do, we need to first hold the ball, and what we do, we move our hand backward, and we make us like a pose. Like if you see the baseball in movies or any game, because normally we don't play baseball that much, but if you see the baseball in movies, so in baseball example, is the one of the best example to show that the person, the pitcher who throws the ball toward the batsman, first hold his hand back, right? Or even if you are throwing a simple ball, what you do? You move your hand back and then you stretch your hand forward and then throw the ball. Is that right? Is that how you throw the ball? First you move your hand back, hold it there, then you move your hand rapidly forward and then you release the ball. Is that how we throw the ball?
Yeah.
So we hold the ball at the back, initial speed is 0. We release the ball with some speed v. So in that duration, what we exert? We push the ball with our hand, we exerted a force for some distance s. And the object accelerated with an acceleration a. So we did a work on that ball of mass m. So the work done is equal to what? Force times the displacement, right? Force and displacement are in the same direction. So what is the force? According to Newton's second law, the force is equal to F is equal to ma. Sorry, I just have to place F is equal to ma. So can I write ma instead of the force? So ma. The other thing, we like remember that the Suet equation technique, 3 things are given, 4th we have to find, 5th is not discussed. So if we look at this data, the same thing is there. We have initial velocity, we have the acceleration, discussing the acceleration, we are discussing the displacement, we are discussing the velocity, but there is no discussion of the time. So we will use an equation without time. Which one is that? V square is equal to u square plus 2as. So what I need? I need s. So what will be s equal to? V square minus u square upon 2a. Is right? So what is u? As we throw in this case, u is 0. Got it? So what we get? S is equal to v square upon 2a. So we have the s value as well as we have the f value already, which we have placed in here. F was equal to ma. So we place that f here. And now we will place that s here, the displacement, which is v square by 2a. V square by 2a. So what we get? We get mv square by 2, which we can write as 1 over 2. Got it? So you can see that in throwing a ball horizontally, the work done is equal to change in kinetic energy. Is right? While lifting the ball, which the work which we did was change in potential energy, and while throwing the ball horizontally, the work which we do is the change in kinetic energy. So you can't provide kinetic energy to an object without doing work, and you can't do the work without moving the object in the direction of the force. Got it?
Yeah.
Is that right?
Yes.
Okay, then there are a few other simple things. Are you familiar with the formula for the power? Write in the chat if any one of you are familiar. What is define power and write the formula. Both things. That's right. So for okay, that's right. That Fatma, what's power? Define power. That's right. So remember, power can be written in both ways because we have mentioned right now that work done is equal to energy transferred. So you can write power equal to work done per unit time, or power is equal to energy transferred per unit time. In both cases, it's joule per second, which is called as watt. And that joule per second is called watt. Okay, but this formula, in some cases, we like modify it and write a new way. So what's the work formula? The simplest formula for the work was force times the displacement over time. So if we look at the second half of that formula, what is displacement over time? What this displacement over time is? That's right, Aisel. Fatma, what it is? Displacement over time. Fatma, what it will give you?
The speed.
The speed or the velocity. So remember that this is also a formula for the power where force and velocity must be in the same direction. If they are in the same direction. Got it? This is what we have. Is it clear? Any question about this power?
No.
Okay, the next small thing which we need for this topic is efficiency. Can you define what is efficiency? That's right, Fatma. I see what is efficiency. Fatma, you need to add one word in the start of what you have written, not just any. Okay, that's right, what you both are writing, but remember, it's not the total output, it's the useful output. Remember, it's not the output, it's only the useful output. Okay, useful output ratio total input. Then this is efficiency. But if you like multiply this with 100, then you will get the percentage efficiency. Got it? Okay, the next thing which we need to do, just because they can use that word, there's a word which is used called Sankey diagrams. Are you familiar with those Sankey diagrams? What is that Sankey diagram?
No.
It's just another way, like a graphical way to represent the efficiency. They draw with the help of arrows. They draw with the help of arrows. How they draw it? They use a big arrow first. And this big arrow actually represents the total input. Then they draw different parts of it. Usually they draw a straight path for the useful energy, that for what purpose we are using it. Then they draw some curved path, like going downward in other ways, that they are the energy wasted. So we represent it in a graphical way, that the wasted energy goes this way. Some of the wasted energy goes in like this heat, some goes in the sound, like that. So that kind of way they draw the diagram. Okay. So usually they pay attention to, okay, I just draw it. Wait a minute. Just not all the time, but sometimes they pay attention to some values. Say that if this value is 100%, you can see that I have almost taken 55% from here, right? It's more than half. So 55% goes useful, and that 20% goes to one waste form of energy, and the rest 25 goes to the other waste form of energy, right? So they do it in proportion of the lengths. Got it? So if that is 100%, you can see that that will be more than half. That's 55%. That's somewhat 20%, and that's somewhat 25%. So if you represent that where the energy, that's total input, and that's useful output, it can be more or it can be less. In some cases it can be maybe 20 useful output if the system is not that efficient. Got it? And that's heat, waste, or other form. So if you represent it in this form, then it's called Sankey diagrams. Okay. Is that fine? So with this, the work energy topic is complete. Next time we will discuss like you can practice the question on work energy from any topical book, whether the one I have sent or if you have any other in the printed form. It never matters. Only thing is to practice. If you find any problem, you can always send me a WhatsApp. I will reply it while when you are practicing the questions. Okay. The next thing is that like next time we'll practice moments. So till now, is there any question from what we have practiced?
No.
So that's it for today. So thank you. Have a nice day. Allah Hafiz.
Allah Hafiz.